around the perimeter of the Arctic Sea, if that's open ocean, even for just a couple months, the opportunities for using those routes for shipping are extraordinary, and we'll talk a little bit later about that. So in many ways, it's not, from their point of view, it's really a question of, is there enough water around the edges of the Arctic Sea for at least a long enough period of time we can count on it being navigable? Then people are going to move to make that, to take advantage of that opportunity. And in many ways, that's what's brand new, right? Because basically, as long as humans have had the technology to think about going anywhere on a boat, let alone taking anything with them, the Arctic Sea has been impassable, right? It's basically been filled with ice all the time. Even at the end of August, if there might be some open water around the edges, but it was not something you'd want to go try to sail through, given the amount of icebergs and other dangers that you would have to encounter. What we're seeing now is a situation in which it's becoming safe and it's becoming predictable. Any questions? So what's going to happen? This is a headline from 5 years ago from the New York Times. As polar ice turns to water, dreams of treasure abound. And the article provided a kind of overview of the commercial opportunities represented by the disappearance of the Arctic sea ice. It said that it's estimated that 1/4 of the world's undiscovered oil and gas resources are in the Arctic. There are lucrative shipping routes. There are new cruise ship destinations. Just what we need. I'm so tired of the old ones. There are important commercial fisheries. And given the state of the fisheries elsewhere in the world, any fishery that's in reasonably healthy condition is worth thinking about if you're in the commercial fisheries business. This has continued. This one is from just this week. Melting Arctic ice clears way for shipping, fishing, oil drilling, and major problems. There was a meeting of the American Academy of Sciences in San Diego this past week, and they had a panel discussion on this subject. And so this is a report about that discussion. An Arctic largely free of ice during the summer will mean new opportunities for fishing, oil and gas production, and shipping in an area that is both extremely sensitive ecologically and highly unregulated. The United States, Russia, Norway, Denmark, for Greenland, and Canada have jurisdiction over Arctic waters within 200 nautical miles of their coastlines. This creates a haphazard patchwork of regulation and is worrisome if countries, namely Russia, have lax environmental standards. So you remember the discussion we had about sovereignty and property and territoriality? This is a case in which basically we haven't needed to worry or think or concern ourselves with property, territoriality, sovereignty in the Arctic because apart from a significant but relatively small number of people who lived up there, there wasn't really anybody who cared one way or the other. The only reason that these 5 countries have jurisdiction over Arctic waters within 200 nautical miles of their coastlines is because that's the rule everywhere else in the world, right? You have jurisdiction, which is to say some kind of legal authority, some kind of sovereignty over the open seas 200 miles out from your coastline. And that's actually a fairly recent extension. It didn't used to be that far. I think it was about the 1970s that the United States decided they wanted to reach that far instead of the previous 50 miles or something like that. And we just said, oh, by the way, we're claiming another 150 miles of ocean all the way around our coastline, and the rest of the world eventually had to come around and say, oh, okay, fine, then that'll be the rule. But previously it didn't matter in the Arctic. I mean, you could put it on a piece of paper, but it didn't really matter. It wasn't really clear exactly where the coastline was necessarily because it was all under ice anyway. So this is playing out right now. There are simultaneously political efforts to figure out what the sovereignty picture, the territoriality of the Arctic should be. That's a source of, or it's an arena of active diplomatic debate right now. And there's also a lot of movement and maneuvering to figure out property claims in the Arctic. And what's useful about this case for our purposes, apart from the fact that it's worth paying attention to global warming, is that we get to watch this. We can actually see this playing out, and we can think about why is it that you need both of these types of territorial maneuvering together? Why is it that you can't really resolve property claims without some kind of sovereignty framework? Why is it that no one really has any reason to figure out a sovereignty framework unless there are property claims at stake, right? You have political arrangements having to do with sovereignty and these different nation states, and you have economic arrangements having to do with property and access or claims to resources. If you want to go tap into some of that oil and gas in the Arctic, and say you're a big oil company, you need some kind of assurance that you actually have a right to do that, right? That there's some place you can go and you can build some platforms and drill rigs and put them all in place and start getting that oil and gas out of the ground. But you need to know that whatever political authority claims that space will recognize your right to be there. And if it's not clear who that political authority is it the Danish government? Is it the US government? Is it the Canadian government? Then you don't really know whether you're going to be assured of your property claims to that rig and that drill and so forth, right? On the other hand, the Danish and US and Norwegian and Russian governments previously didn't really need to care about this area because even if there were lots of resources there, you couldn't get them. You couldn't get to them. So they were, in effect, not there as far as needing to resolve sovereignty questions. So this fitting together is what I'm getting at. Okay? Other questions about that? How many of you have taken a class in global warming or feel like you have a solid grasp of why it happens, how it's happening? So just a few of you. Okay. I thought that might be the case. So here's a little side detour into the question of global warming more generally. And here again, it's useful to think about this in terms of the temporal scales of the processes involved. So here, we're doing big, huge temporal scales. These are graphs going back 400,000 years, depicting temperature change in the bottom graph relative to normal, relative to the present, in centigrade. The top graph over the same time period is CO2 concentration in parts per million, which has been reconstructed from the Vostok ice core. This is another reason to care about the Arctic, or specifically to care about Greenland. All that ice turns out to be the best known repository of data about the Earth's atmosphere for this kind of time period. Each layer of ice got laid down in a given season, right, a given year. They're layered just like the layers of sediment in a floodplain, perhaps also comparable to layers of tree rings in a tree. And inside of each layer of ice are little teeny tiny ice or air bubbles that got captured in that ice. And the air in those air bubbles is unchanged from the point in time when it was captured in the ice. So we have 400,000-year-old air in these bubbles, and we can analyze that air and figure out how much CO2 was in the atmosphere in each year, or at least in intervals, very fine intervals, like a year or 5 years, that kind of thing. And because all that ice has been forming and building for such an incredibly long period of time, we've got a record there that is remarkably intact, remarkably reliable, and it would be a shame if it all melted away and we didn't have the data anymore, right? It would be a loss to science. And the best ice cores have been found in Greenland, the most intact and the oldest. I believe that there may also be some very good ones in Antarctica, but a lot depends on how well they've been laid down and preserved over time, and then also how easily we can get there and actually drill these things, because you have to drill like a mile or more down into the ice and pull the whole thing out and take very good care of it. Anyway, you can see from looking at these graphs that there is a remarkably consistent, tight correlation between the amount of CO2 in the atmosphere and the temperature of the Earth. Okay? This is just to demonstrate that we know this not only from first principles of physics and chemistry, but empirically, going back at least 400,000 years. Anybody know which one causes the other? It's a trick question. We know that they correlate, we know that they are related to each other, but we don't really know exactly what the principal driver or causal force is. In other words, we know that when CO2 concentrations go up, as they have at various points in time, temperatures are also high. And we also know that CO2 concentrations are rising now well above what they have ever been in this time period, right? So the highest CO2 concentrations we see in the last 400,000 years from the ice core were about 310,000 years ago, and we're just about 300 parts per million. What is the CO2 concentration in the atmosphere now? Anybody know? 384. That's about, yeah, it's somewhere between 384 and 387 right now. So we are already well above any level that's been seen in the last 400,000 years. On the other hand, that's not to say that we know that the rising CO2 somehow caused the rising temperatures previously. That's a fine point. Perhaps doesn't need to be belabored right now. Any questions? So here's what's going on in the last 150 years and also over the last 1,000 years in terms of CO2 concentrations in the atmosphere, again, parts per million. You can see that it hovered between 280 or 270 and 290 for the better part of the last 1,000 years. It started climbing in the 1800s and in earnest in the 1900s, and is now, it's actually higher than that graph now. It was at 360. It's going up about 4 parts per year right now, parts per million per year. Over the last 200 years, you can see the ice core data is what gives us these numbers until about 1960, 1956 or 58, which is when we started measuring this directly in Hawaii, and you can see how it's climbed since then. All right, shall we take our break? All right, 5 minutes. Okay. This is the famous hockey stick. But actually not a hockey stick. They call it the hockey stick because it looks kind of like a hockey stick. This is Northern Hemisphere temperature anomalies relative to 1961 to 1990, which is just to say, compared to the average temperature between 61 and 90, which is the line through the middle at 0, what have the temperatures in the Northern Hemisphere looked like over the last 1,000 years? And we can see that they've gone up and down. The black line is a smooth sort of average through all of these data points. The reconstruction from 1,000 to 1980 is based on things like various kinds of proxies, such as those ice cores, that give us ways of inferring what temperatures were like in different parts of the world at different points in time, going back in time. Tree rings are another, that sort of thing. Actually, the shells, teeny little shells embedded in sediments in the bottom of the ocean are another really good way to reconstruct these. You can see the gray is there to indicate sort of the range of blurriness in the data. In other words, how much uncertainty there is, what the range might be within which we are comfortable we've got this nailed down. And of course, the further back in time you go, the larger that range is likely to be just by the nature of the information available, right? So as you can see, as we get closer to the present, that spread gets smaller. We can see temperatures going up and down. There's been significant variation in temperatures, but on the order of half a degree centigrade. And then in the last say 30 years, we actually can just, or actually I'm sorry, last 100 years or so, we can rely directly on instruments, measurements of temperature that were recorded over time. So the error or uncertainty becomes very small, and we start to see the temperatures climbing towards the end of the 20th century, and the continuing to climb now well above not just average, but anything that was previously considered to be within the realm of possibility for the last 1,000 years. I shouldn't have made this so big, perhaps it's too blurry, but reconstructed temperature, again, over the last 2,000 years, various data sets generate different lines here, but they tend to move more or less together up and down. The medieval warm period is a period of time when temperatures were a little bit warmer than normal. It was followed by the Little Ice Age in around 1600, a period of time when temperatures were a little bit colder, and then rising very significantly again, much higher than anything previously recorded in this time period. Those are all averages, right? That's averaging for the Northern Hemisphere, or averaging for the world as a whole. But obviously, the effect of this is not the same everywhere in the world. This is a map depicting the relative surface temperature changes over the last 30 years or so in different parts of the world. And as you can see, it's the higher latitudes, especially in the Northern Hemisphere, where temperatures have risen the most. And this is what's already happened, okay? So we're seeing a rise of 2 to 4 degrees centigrade at the Arctic and much of Northern Asia, Northern North America. There are other parts of the world that have also seen that amount of warming, such as in Africa and the Amazon. But then over the oceans, you actually see that temperature has been stable or even dropped in the same time period. Or not all the oceans, but some of the oceans. And in most of the temperate world, the rise in temperatures has not been as pronounced as in the Arctic. And this is why, again, it's worth using the Arctic or thinking about the Arctic as kind of further along in this process of warming and therefore illustrative of the kinds of things we can expect. It's also worth just noticing that the parts of the world where the wealthiest, most powerful people happen to reside are not the parts of the world that are going to bear the brunt of this in the short to medium term. The worse implications or the faster changes predominantly are going to occur in parts of the world where people are either not very numerous or not very powerful, or both. This also can be thought of in relationship to precipitation patterns. Here we get change in overall average annual precipitation 1976 to 2005. The red colors are areas where precipitation, rain and snow, have declined. The green areas are places where it's increased. And you can see, again, it's not at all evenly distributed around the world. So much of sub-Saharan Africa has seen a decrease. Much of the Amazon and South America have seen a decrease. The western and southwestern United States have seen a decrease. But in northern Siberia, northern Russia, a lot of other parts of the world, you can see significant increases. It's interesting that there are places in Asia where you've got significant increases right next to significant decreases, right? Which has to do with the movement of the monsoon patterns in relationship to atmospheric pressure and temperature. So the oceans, which absorb roughly half of the CO2 that we've emitted, are in the ocean, rather than in the atmosphere. Temperatures in the ocean are changing. That has significant implications for weather patterns at global and sort of continental scales. Just to emphasize again, this is it's an unequal process, even if we frequently think of it in terms of averages over the entire world. All right, questions? Yeah, that question? Well, I mean, it depends which kinds of effects you want to focus your attention on. In terms of agricultural productivity, for example, agricultural production, the studies have found that the more severe impacts to agriculture from things like droughts are likely to happen in lower latitude places, which tend also to be already more precarious in terms of drought and water resources, and also tend to be poorer countries with less money available to do things like drill wells and put in irrigation systems. So the impacts to agriculture are expected to be more severe in the poorer parts of the world than in the wealthier parts of the world. And there are even parts of the developed world where rising temperatures might actually benefit agricultural production. So if you think about parts of Canada, for example, raising temperatures 3 or 4 degrees would mean much longer growing seasons, might not mean reduced rainfall, might enable them actually to grow crops in places that previously couldn't grow those crops, that kind of thing.